Hello and welcome to our technical webinar from the series of Simple and Accurate with Allplan Bridge. Today the focus will be about choosing the appropriate modeling method for tendons. My name is Gottfried Grabner. I am technical consultant at Allplan Infrastructure here in Graz, Austria. During the webinar there is a chat function active, so if you have questions during my presentation, please write them in the chat and I will answer them at the end of today's session. Now to today's agenda. In relation to tendons, I would like to start with some basic principles and after this show you main modeling approaches which we do have in our solution. And after this, then I would like to get to some tendon point definitions which are possible to be used, and then I come to the two big parts actually. First, straight tendons, how to define them, adjust them, modify them, how to set the parameters to get good and nice results which you want. And then I would like to do the same for the curved tendons and also some more things which are possible in for curved tendons. Then I would like to do demonstration. I would like to show you examples, and I want to show you some workflows in order to make your daily work life with tendons, tendon modeling and so on even easier in future. And for closing up, I do have some projects here from clients and from partners which I would like to show you some parts out of it. Okay, for the basics, the tendon definition is like this, that we have reference points here, just put some in green here, and these reference points are the base. On top of this reference point we create the tendon points with some eccentric offsets and get then the tendon alignment out of it. So here in red are the tendon points, and then with different definitions, eccentrics, tangents, offsets or angle constraints, I get the tendon alignment in the end. All in all, the tendon itself is created as a spline, and the spline is of third order. But so much for the startup. I get into the details later. For the reference points themselves, it could be reference point or it could be point grid, which is actually a group of reference points. This is the base for at each cross section, and on these points then on top further definitions are done to get the tendons in the end. The main modeling approaches here we have like this, that the tendon can go through the 3D tendon point which is defined, so directly go through, or it could be like this, that the 3D tendon point is the base for tangents, and then the curve itself is created via these tangents definitions. Okay, for the first case, when the tendon goes through the points, here in red I have the 3D tendon points. They are set, and then the tendon is automatically by the software created along and through these points. So the user defines in this way the tendon, but what it is when the user wants to have the option tangents. In this case we have here the example from before, but now for the tangents we create between the 3D tendon points tangents, and then a radius is defined for each curve, and with these definitions I can create also a spline out of this which fits to the tangents and fits to the radius which is defined, but it does not go through the tangent point anymore in these positions. Okay, here you see the comparison, like one way of curve what is coming out when I take the spline directly through the point in his first approach here in red, or if I go with the tangents I have a different alignment. But it depends on the user. We provide both options, and the user can choose which one fits best in the individual cases to be used. Okay, also there can be a mix of this be used. So here first the spline going through the points, second what we saw already going with the tangents and the radius, or it takes at the first point the radius and the tangent option, and at the second point here it takes directly to go through the point. It's also possible. Okay, as next point what I want to show to you is eccentrics. So from a reference point I can put eccentrics and create out of this tendon point. In this case, several stations are shown with certain positions of the tangent points, and then this tendon itself is going through it. But what happens if I want not directly to be in one station to have a certain point definition? I can do it like this, that I define an EX center, so move this tendon point in longitudinal direction, and what will happen is after recalculation the tendon will fit to the new position. Same thing for the extent I can do also in Y direction or in Z direction. So here, for example, this is profile view, several stations, several points, and the spline going through it. I take EY center, and the spline will go in this point accordingly to the new position at recalculation. The other points, for sure, as there are no definition changes there, they will keep the same as you can see here. Same applies also in the plan view. If it's the same principle in the plan view, if you apply a Z center, it will move then along the new position. So for other constraints, angles in this case, I can do the same. So here I have the same basic model, points with the spline on it, and if I apply here a certain angle in one of the points which is different to the natural angle which the software is calculating, I can do this. I can set this constraint with alpha v in this case in the profile view, and then at recalculation the spline will be set that in the starting point it has this direction, and all the alignment will adjust accordingly. In EZ direction plan view, it's the same way. Okay, I have here some specific key points now, which I want to show you. There's some topics which are of interest, and they are not so commonly known. One point first, high point definition. Then afterwards I want to go a bit into the angle constraints. Then I want to get a bit into the tangent and the radius once more. And then I want to show you one transfer option for the tendon, which is not that known, but it's convenient in several cases. Then I want to go a bit on the tendon properties and on reporting and outputs. Okay, here for the highest point definition. I have here one example. You can see it, it's in the software itself. The tendon itself is here defined by 3 points at 3 stations. It's fitted onto different points of point grids, and there are no excenters or anything like angles or something defined. So what happens is out of this definition here, here, and here it's fixed. It gets a certain alignment, but here it gets very close to the surface, and this is in this case not wished by me. I want rather to have it like this, that I have the highest point here in this area, and that it not got further out. So I can set this very easily, and it's done like this, that I get in here. I get to the second point where I want to apply it, and I can fit it in here or in here on the right side in the properties, that I set this alpha v, so the angle in this point is 0, so parallelly here to the surface in this case, or horizontally in this case. And then after recalculation the alignment is changing accordingly, and I have in this case, as this is a horizontal tangent, I have in this area the highest point. Okay, here also something about the angle constraints, how to adjust it. It's also happening here on the right side. I go to the individual station where I want to fit it, and I just have to untick it and then give a certain specific value what I want to fit on. In this case, you see it's the same example like before, but here in this area now adjusting the direction at the beginning gives us a new result on the alignment after recalculation. As you also can see, this horizontal tangent is still in place. That means this highest point is still here, and only the definitions here along are adjusted now according to the new angle in the beginning. This is all very easy, very quickly possible, just a few clicks and recalculation, and by this you can set the individual constraints about this, in this case on these 3 points, and the tendon would behave as you define it, as you want it. So you come very quickly from a very initial phase of tendon alignment where you say, these are the main points, and then I fit with excenters, or fit with constraint with angles and so on. More and more definitions on top until the final alignment is then properly in. Okay, here I have about the tangent and the radius definition, one more thing. how to set it in Allplan Bridge. It's the same thing. I use now this point here again, and just went to the properties, and instead of a spline, I choose here to have a tangent. And when I have this placed, then automatically here it asks me for a radius, so the radius is unticked. It's not free anymore, and it's to input. So I choose a certain radius and recalculate and get according to the form. And as I choose by purpose the radius as a very, very small one, I have here this edgy form, but actually it's a spline which goes here then into the radius and then goes here again, main this in a nearly straight form then to the next point. So this is how I wanted to have it here, but more common it is like this, that I have an individual point, which is, just to show again, the point itself here, which is used a space for the tangent is up here, here, and then with a bigger radius for sure. Out of this point here is one tangent, here is one tangent, and then the radius is fitted nicely in to the form of the tangents. So yeah, this is also one input, 1 to 3 clicks and recalculation, and then you have already a new form how you want to have it. Okay, here I have another transfer option. As you can see here, it's shown in Allplan Engineering. There are some tendons in place. They are fitted. They were transferred out of the parametric setup from Allplan Bridge, and they have normal tendon setup. But here in Allplan Bridge, I go now in and define all the tendons with a diameter of 0. So as you saw, I marked them all and define duct diameter 0. And you see in Allplan Bridge, the duct diameter is changing, it's getting smaller. But what happens when I do now the transfer to Allplan Engineering? It takes a few seconds until this is transferred. The thing is, the tendon themselves, they keep their location, but with the diameter of 0, they will be not shown as tendons, they will be shown as lines now, which is very convenient in certain cases. So I just switch off the model, the bodies, and I have again the remaining tendons. And now you can see there are individual lines in which are defining the axis of the tendon. So if you want to have this and want to do this, you don't need to check it out. You just have to transfer it one time to Allplan Engineering, and then you have lines in there which you can, or these lines, the axis of each tendon in there, which you can make further use out of it. Also, if you want to have both the axis in Allplan Engineering and the tendon itself shown, transfer it one time with duct diameter 0, then you have the axis in there, copy all these tendons into a different project document, and then do the transfer one more time, and you will have then both things parallel in the project. It's very convenient, but most people do not know it, so I wanted to show you at this place. Okay, here for the tendon properties, something, as you can see, most of you I think know, we have the normal material properties here with different strand area, we have friction, deviation, definitions which are needed more for the analysis model later on. But also one thing here, straight at begin and the anchors here. I want to show you one thing. So we can go in if there's an anchor block or a couple or something needed to be placed. We need a certain straight alignment normally in there, so it cannot be curved. And this is just by clicking onto the tendon and defining a certain distance here straight at the beginning or at the end of the tendon, and the program will automatically model a straight line, and then it goes directly in the spline alignment in the curve as it's defined. This is how quick this is set actually. Just put it on. Also multiple adjusting is possible, so you mark all the tendons and you put it in one time and you have it after confirm with enter. Here downside you can see there are certain elements in there. It needs two things. It needs in Allplan Engineering, you define a smart placement with a certain name, and this is in this case anchor. And this smart placement is taken in and put automatically in the beginning of the tendon or at the end of the tendon if you place in Allplan Bridge the name of the smart placement in here in the tendon definition. Then you do the transfer and you will have at each tendon where you define this automatically the smart placement on location and direction on the place where you want to have it. Okay, for the tendon properties, the material I noted before, Here is already for the outputs of the pre-stressing. If I have inputted the material, if I have inputted the area of the tendon, the alignment and all these things, I can let then with the tendon model, with the pre-stressing model, I can let the program get the output out of it. So one thing I also have to note, as user, I have to input first as stressing actions. So timely, I want to stress. I want a wedge slip is then happening. I want to stress then later also in the end of the tendon, and again a wedge slip is there. So I have to do the actions of the stressing and the tendon installation. But then at calculation, it will give me the stressing diagram, as you can see it here. Like I have the stressing at the beginning, get this diagram. Then I have a wedge slip. I get here to this line. Then I have the stressing at the end to 100% of the capacity. I get up here to this line, the wedge slip here, and then you can see here in the red line I have the resulting stressing diagram for this individual tendon. And in this way, actually for each tendon individually, on the alignment and on the definitions of the user, the output is here in the program given. So if you need this, it's very easy, quickly also on hand. Same thing also is here in the output report. So if you need it, you just need to give some comments, and then you get the PDF file as output with this calculated values and forms. Same thing also for each tendon. The geometry definitions can be exported as a PDF file and can be then used for job site or for the office where you need. Also, we do have another option here. For each tendon, I can use the command or the function actually, which is called tendon report. How do you come to it? You go to the tendon itself, do a right click on it, or you go to the face or the group of the tendon and right click off it, and you find then on top of the other options where the tendon report. If you click on it, you get a new field for input, so for choosing. Here you choose what output elements you want to get from the tendon. The most common one is the geometry, so if I want to have the geometry, I tick it. Also, if you have analysis functions in the project with results already, you can do an output of forces or the engagement on top of it. Yeah, this is mainly what you want to get. Also, here are some definitions. If the geometrical location should be in reference to a certain reference point in the project, you have to give here the name of the reference point or the name of the point grid, and then it will get the locations fitted onto this user-defined locations. Here's what step along the tendon should be for output. So each 20 centimeter there is an output value generated, and there's the file name. What is then the result? Here you can see the result is an Excel table, which has first of all the point of origin. So if nothing is defined, it's the project, it's axis, the basis. If you define a reference point, the XYZ for the reference point, each 20 centimeter along the station will be coming out here. And on the right side, as you can see, we have chosen here the group of tendons. So each tendon actually shows then the station plus a Y and the Z center to this origin point. So by this, the geometrical location of the origin, but also of each tendon, is directly in there. If you want to have the XYZ from the tendon, it's also very easy possible. Just go on the right side, do one column where you add up the Y values, Z values, and automatically then you have the XYZ then only for the tendon purely. Okay, so much for these points. I would like now to get to this to the type of the straight tendons, how to model them. Different approaches, and the first approach here is that the tendon point is directly in the reference point or in the point grid set, and this reference point is keeping its position in the cross section, so no variation or something is on. So here the example to it, so it needs actually in the function one clicking here, getting on the station the point definition, reference point 1, as you can see here, is here chosen, and here at station 25 also reference point 1 is fitted. One recalculation and the tendon is straight inside the model. Few seconds and it's done already. This is how quickly actually this goes in here. The other approach is like this, that it's not fitted directly on the reference point, it's fitted in relation to the reference point or to the point grid. That means I have the reference point, I apply to each point or each station and the point I apply center, and then I get the tendon point out of it, and out of this tendon points I get the tendon alignment calculated. Looks like this, quite the same. I have a straight tendon which is fitted between the point at station 0, here reference point 2, and also here reference point 2 at the station 25, and it's a straight alignment. In the same way, I could go over here, choose another reference point with other eccentrics on station 25, for example, and the program, if it's only 2 points, it would get me a straight alignment in between these 2 points. So very quickly on the point where when you have straight tendon alignments on different positions, it's just a few clicks and done. Okay, what is it if I want to create curved tendons? The approach, also I have different ways. One way of approach is that I have a tendon point which goes through different reference points, so it's not always the same point at different station. I have at each station a different point, and so it's a different reference what is used. It's from the way of doing it, it's not so much more steps to do. I have here one station at 0 where I've chosen here a point from a point grid, here downside a space, and I get this point out of it. At the station 5, I can see this is the point 1, 3. This one actually here in the cross section is a base point, and then I get to the station 25. I create another point, and I take now this point here as reference. So this geometric locations are taken from the cross section, from the reference points, and then as you can see here on the right side, there are no eccentrics defined. So it will go then and create these tendon points directly on the reference points and create the tendon alignment in this way. Very quickly, very easy. Just there are 3 points now, and in between these 3 points is a curved alignment and fitted. For sure, also it's possible to define on much more stations certain points. If you need it, you can put this constraint and it will accordingly create the alignment for you. Okay, another approach is that I have the tendon point relative to the reference point set, so the eccentricity of the tendon point varies. We have had already quite something before noted. Here one time more with some more details. So as you can see here, I have a tendon alignment in there, and this tendon alignment is fitted on each cross section in between here onto a reference point. And here you can see it's always the same reference point which is chosen. It's always the reference point here. Here's the base, and here's in U and Y direction. The Y direction is eccentric seeable. As you can see, we are here at station 20, station 20. The reference point is here downside, but up here is the tendon point, because there's an eccentric of 1.4 defined, plus in this case also there's this alpha, so there's horizontal tangent here defined. These are the 2 constraints, here the eccentric and then the alpha constraint. And out of this, the tendon alignment is created here along this way. One thing what is important in this example is also that here the eccentric in V direction, there's at one place at station 20 this set for 1.4 meter, but for the other station we can see here this is set for 3. So there is no fixed value set. That means here where it's set for 3, in vertical direction in this case, the program will calculate and interpolate this spline alignment from here, this is one point which is fixed, to here, and then it will accordingly calculate in vertical direction the positions which are used here. So in this way it's also, you can set a few constraints. If you have it in horizontal direction properly, you know where it is, so you have no eccentrics there, and you fit it onto the position. But in vertical direction, you know only here you need that 1.4 eccentric, you need to be at this position, but for the other locations you don't know it, and you don't need to calculate it in this case, because when you set them for 3, the program will calculate it in vertical direction automatically for you. This is one way of modeling, but also you can even do it easier. If I have a little look, I have the same thing in the geometrical model. It's the same result. I have done it only with 3 points and get it. I have the starting point, I have the end point, and I have this point with the constraint of alpha is 0, and with the eccentre in v direction of 1.4 meter. And if I just look in between these two, it's a bit under perspective that the differences, but the tendons have the alignment, you can see it's the same output result in the geometry. The difference why I wanted to show you this one is simple. In the geometry it's no big difference, but in the analysis it would be different. So when you want to go with your model and create an analytical result out of it, means pre-stressing, inner forces, or also like in construction phases, then you want to get there further and further along, then it matters. Then you need to think, okay, where you want to have the tendon link to the structure. Do you link it to each cross section, or do you link it only to a few of them? This depends then on where the outputs will be more in detail or less in detail. So this is what I want to give you along at this point also. Okay, another approach what I want to show to you is here the tendon point can be set also directly on the reference point on the point grid, but this reference point now itself varies. So how is the whole thing done? We go to the cross section, we have a certain reference point fitted, and this reference point is with a certain distance to a reference line here, a parametric line set, and on this line I define a variable, and then I can use in this 3D body the possibility to put a variation table on top of it. And in this case, to this distance here, I choose to have this eccentre alignment, in this case then shown like at station 0 up to station 25. I want to have this parabolic approach and this parabolic alignment here for this eccentre placed. This I fit onto this variable, and I get in this 3D body then a setup where this reference point goes with certain positions here along. And as the tendon, as you can see here, it's fitted always to the same reference point here. This one, this reference point varies. It gives automatically this parabolic alignment, and also for the tendon. Here I do have another example for you now. As you can see, a couple of elements already, the piers, the bore bias and so on, some supports, reference points and so on. And there are some link girders in between here, which have this cross-section shape actually. And here 2 point grids are defined and the reference points. And based on this, I would like to go with you and then create some tendons in these structures and in this precast element. So as we had before also already the straight tendons, let's start with this one here, how to create it. I can do it directly point by point, so just select the member starting station at the point, and same thing for the end station. And I have already a straight tendon here in place now, 2 points defined, and in between there are set. Same way I can do it that I create this straight tendon with points and an eccentricity. So I can go in here and say, let's go at here, starting at this one, and I go up here with 0.05 and 20 centimeter upwards. So have the first one created. And I do the same here on this one, 0.5 horizontal and 0.2. So, and I have another straight tendon here created, and as I look now here further in, I can see it here also on this one here, it's with an eccentre. I can see the eccentres here or also here, plus also here. Well, you can see I have the reference point, and then with the constraint I get to the tendon point actually, and where the tendons fit up. Both of them are straight. Actually I could also get in and say I want the second point get to 0.3. I just need to recalculate, and it's still a straight tendon, but it has now an inclination in relation to the beam itself. So here it is. Also same way I could just a few things. I can here say, for example, I do copy move, same group, and the station, it should copy me the straight tendon to the right side. So here I have it, the new one. And I can adjust this one also in the way that I go in here and put some eccentres at the first point, for example, and recalculating gives me already the new form and alignment here now in the 3D. So this is how quickly you can adjust and fit things. There's also another option here to create, in this case, a starry tendon. I can also choose to create a tendon between two stations. So same like before, I choose the girder and then it's starting station and the end station, and then I have to choose the point, and now I have another tendon here in place. Here, as you can see, it's now this one. After recalculation, also it's color marked because the alignment is then calculated and set in the 3D properly. Yeah, here I have this one, and you see it takes every cross section here, and if I don't want to have this, for example, in the middle, I just go in here, delete it, and I have straight tendon without eccentres here also placed in. Okay, so much for the straight tendons. Let's get to the second big setup for the curved tendons. I showed you already a bit before, but now let's go and create some. I would say I'll give it another group. And then, yeah, I can do it also reference point with eccentre. So first way, go in here, choose here station and the point. For example, I can choose this one, I can go with this and the eccentre further inwards, or I take this one and, for example, take 0 as horizontal eccentre and 0.3 as vertical eccentre. Just for the first run here, then the center point, I keep 0 and 0, so no eccentre at this one. And actually I see, this is not so much, I want actually to have a bigger eccentre here at the borders at the end, so anywhere here up to, let's go 1.6. Oh, I had the wrong one, so here 0 and 1.6 vertically. And I have the third point set. As you can see, the first one I have to adjust a bit, so 1.6 on the first point. After recalculation, I have my curved tendon here in place, as you can see here, with the eccentres vertically at both ends, and in the middle it's without an eccentre, and I have the curved form with the spline in here in place. Yeah, for example, I don't want to have a spline here, or I have a certain constraint where a certain radius is placed here, and this point should be taken as a tangent. How do I do this? It's quite easy. I just go to the respective point. So this is the point here in the center, and I choose here in the properties not the spline. I take the tangent and I set the radius what I want actually. For example, if I want to have a very small radius of 5 meters, set it here, recalculate it, and now you can see it's looking a bit more like V-shaped now, because the radius is very small. And in this case, you can see that 2 points created also here along. There's this part in between with the 5 meter radius, and then it goes smoothly into the spline section here and here. Yeah, I can go in and say I want to adjust this. The radius is too small, I want to have a bigger radius of 50 meters. Oh, you can see here the 2 points, they go further out as the radius is then fitted up in a bit different way, or not different way, but the intersection between the spline and the tongue, and here the radius point is getting further outside, and like this I can set it however I like it, and now you can see it's not that V-shape now, it has a rather curved form in place. Yeah, so much for this one. What more? Yeah, I also can go in and say I want to work with individual points, no eccentres. I go in here like, for example, take this one, starting point. I want to get up here with this one starting, then getting in the center to this grid point, and then in the end again up here, recalculating it, and let's look on the result here. Now you can see it has this curved form properly in place, and it goes here from the upper edge, the upper end also here, and I don't want to have this, so I can adjust here very simple. V direction, I go further downwards. For example, it goes 40 centimeter at the end points downwards, recalculate it, and you see how quickly this is adjusted. So if I also go and view in here, I can see this tangent or this spline, they have a little bit differences than in the alignment, but this is the thing, you can do it in different ways, and however you want to have the resultant set, you can do it in this way, what fits better for you. Another thing also here at this point, for the constraint of the angles, I can also say if I want here for a certain angle here in the end, or for example I want to have it horizontal, just go to the respective, in this case it's the V direction, alpha V. I set this 0 in the end here, and also set it 0 here, and as you can see I have now here a horizontal tangent in there and in there. Also another thing what I mentioned, but here I can go for the endings, for the beginning and in the end of the tendon. I can go in and define a straight length, and after recalculation I have here additional points. I just show it here on this side of an additional point, and this is straight, and then it goes smoothly into the spline alignment, and yeah, this is how quickly you can set also this details if you want. And yeah, as noted already, if you have a macro in or a smart part in Allplan engineering set, write the name in here and it will place it then at the end of the tendons if you want to have it. Yeah, I want to show you now another another way how I set the tendon. For this, actually I want to go one step back. I create another girder here in this case. So this one actually just need to go to the 3D model and drag and drop the template here in, and let's name this girder 2-3. Yeah. And then I just need to define okay, starting point and end point. This is the big advantage of the link girder. I define the points and the program automatically fits them onto the locations. So okay, I have a new girder, and on this new girder I create a new tendon, and this tendon I do it between two stations, but I have to do a global recalculation first, that the girder is completely modeled and in place, and then I can base on top of this one my tendon. So I want to have it here, I want to have it from this station to the last station, and in this case I want to have it go and running through this reference point, and you see there's quickly the points are created and the reference point is all on the same height, so it's straight tendon in this place now. But actually I want to have a curved alignment here, and so I can go in and put eccentrics here in the tendon, but I want to show you this different way also. In this way it was done like this, that I have here this vertical offset of the point I have here set with the variable, and on this variable I want to place this variation table what I have prepared already. So you see this curved alignment setup, and here are some settings for relative stations what I can place then on the girder. So when I go in here on the variation, I have here already, because I have created here this variable, I have here possibility to manually input the values, or I drag and drop my table over here. I define what station types I want to use, in this case relative station types, and you can see here values are fitted already. So I recalculate here, and then I can check already on my tendon in this place, and as you can see here I have this curved form now also already in here, but in this case it's the reference point is here, here, and here, and the tendon is fitted already to the reference point without any eccentrics in the tendon. So the eccentrics are actually coming from the variation table on the reference point. So when I want to adjust something on this, I would need to go here in the table, adjust the height and everything, recalculate and have it then in place. Yeah, as I've seen it, also the program gave me some warnings. It failed to calculate me the direction at the end point of the tendon. It's very simple because I went quickly in at here in this case at the end of the girder. There's the back section, is the key point where it is to set. So this I just need to have to fit up in a quick run. And I do a recalculation and the warnings are gone. So you see, whenever I miss something or whenever there's something what might need attention, the program gives you a warning and error, and you can focus on it, fix it, and also quite quickly, as you can see right now. So yeah, so much for this example. One thing what I would like to show you also, it's like this combination of the precast elements or this link girder elements and the tendon and so on. It has a lot of conveniences. As you saw, I can drag and drop these templates in and use them on different places. Makes it easy to handle and quick to draw these elements. So it's a lot of time saving in here. Or also, if you want to adjust something or want to fit something, for example, I have this girder here and I want to use this girder on a different place. And focus here, we have 42 meter span distance on here on this length, and when I look on this girder, it's also 42.16. So let me have a look. Yeah, 42.37 and so on. So there are slightly different distances on here. So what if I want to have this girder not here, I want to have it here actually placed? It's no problem. It's actually, I just have to catch the girder and I go over here where I adjust what reference member it is, where is my starting point. For example, then I take this 406 and where is my end point? 406. I could do this and I do a recalculation, and now you can see this girder is already in place. Maybe also adjust the name, and I think adjusting the name takes nearly longer than replacing this girder. Now looking onto this, the girder is here. Also the length has changed already automatically to the new positions and reference point. So this is how quickly you can fit the girder, or also it's possible to do here multiple copy or copy of this girder, so it's quickly on creating these models for the girder itself. But I moved and shifted the girder, so what happened to the tendon actually itself? In some programs the tendon remains on the old location, but no, here not. As it is parametrically linked to the girder, you can see the tendon, what is created, is still in the girder. And let's look here, I think was the tendon number 2. Yes, you see, it is still in place. It has adjusted to the new lengths with all the definitions. The straight element is here, the horizontal length is here. So all the things automatically adjusted to the new position. So this is also, if you use this and adjust this and fit this to new locations, you're very quick on handling, because quite a lot of elements are taken over. Not everything is taken all the time over, but many things. So what gives you a lot of time savings in the end. Yeah, so much for this example, and yeah, let's go on for the next. Another example, as you can see, it's a plate bridge going over several spans. Cross section here has the definitions what you need already inside. Also, as you can see, there's a point grid on the bottom, horizontal, and a point grid on the top in the inclined version. And this is the base for tendons afterwards. Also from the settings in here, there's already one tendon created. As you can see, it's set up in a curved shape. Also, it's mainly fitted on the point grid on the top, and here in one station at 25, it jumps up to the point on the top. Also, there are eccentrics defined, and some points are defined as free, so that the program automatically calculates the location at this step, at this point. Also, everything is defined as spline, as you can see. Okay, for this one, first of all, if I click on the tendon itself, I have here the possibility on the right side to do the material definitions and so on. And also I can define, for example, here with the naming of a smart part what I have in Allplan Engineering, I can name here, and then at the transfer automatically the smart part is shown. For example, here an anchor or also a coupler could be here in the end. But the key point is that these names which are written in here are in Allplan Engineering defined as a smart part, and on the smart part you have the model what you want then in there, and it will automatically attach it. Also, when for anchors or for couplers you need some straight lengths when there is especially quite a small radius here in the tendon, and this can be done here to define a certain distance straight in the beginning and at the end of the tendon. And if I look here, recalculate again, then I can look on the tendon and you can see additional points here, these gray dot points. There's here a point in, and the first section is now straight, and also here the last section here is straight in between this section. Yeah, this is one of the possibilities. Yeah, also if you want to adjust certain elements, like here, move something not completely on this stage, move it a bit further to the side, and it's also possible in the vertical direction, this is the V here in this case, in U direction, in the horizontal direction, also in longitudinal direction with EX to move it further on or backwards without creating another cross section or station actually. Yeah, okay. So what can I make out of these tendons? I can do a couple of actions. For example, I can multiple copy and move this tendon in the same phase. Let's do this a couple of times here. This on the first point, and let's get this on the third point. And I have a couple of tendons now created over the whole length here, as you can see. Also, if I want to have, okay, here in this case, this is the first phase here of construction, so this span is set, the tendons are installed, and then it goes further for the second span and for the third span. So for the second span now, also let's create some tendons over here, and I would like to use this as a base, what I've created already, so I just need to do one time copy and move. I put this already to the phase 2 and give it the appropriate name, and I choose the copy station and position, and there is already a base for the phase 2 tendon. So I have this here, so it's about extending it here further along, and I can do this here with the function station between 2 points. So this is first, and I want to go to 60, yeah, and the location is this one, and I go out of the function, and as you can see, it just fitted me now these tendon points onto the reference points. So, and here the extended table. Everything is straight, everything is put on the point on the bottom. So I would like also to fit this up here now in this area. So at 55, same, I jump here up to the upper point, recalculation and check on the form, and now I have to fit it a bit here in this case. First of all, V direction 0.35. Further up here, and then I get in with these points and also set these ones next to this highest point at 55. Oh, not the alpha, I need this one here to set on 3, and then the program can calculate the alignment based on the spline, and I just saw here also this point. I did it in the wrong way, so, but no problem, it's parametric, it's easy to fit up and adjust. And as you can see now, I have here also already the tendon going further on the top, and yes, so in this way I have already quickly a tendon model here in place for the second phase. If everything like this is fine for me, I can do again the multiple copy. And usual way, first station and point location, naming it station and point location. And that's it here for the first two spans. Actually, tendons are in, are fitted, and so on and so. Now it's about fitting up here. Third span also what kind of tendon or how I want to place the tendon and everything. And we have here different options, but I want to show you one way how it can be done. And this way, it's like this. I use the, I would say, let's go for the copy and mirror function. In this case, I can choose also I want to place this tendon now in the phase 3, and it should be tendon 3, the 1. So now it's properly written also 3, then 1. And I give it the mirror in the starting station. In this case, here at 50 it should start. And that's it. As you can see, it took the tendon here from the left side and mirrored it and defined the first starting point of the tendon, and I have the alignment here in place now as tendon 3-1, and definitions are taken over, and there's quite a lot what I can make use of it now, and I just have to create a few points in between here, and yeah, let's do this. I can use again this function, tendon point between two stations, so from here to here I want to have tendon points created, and this should be here on this point, and so, and I just saw I missed here one point, but it's no problem, just need to fit one more. I should have started directly here, but let's create this point. Tack, here we go, and recalculation. Look on my tendon now, and as you can see, it was just fitted directly on the point over here, so a little bit fit up is needed. As I can see here, the last point is here with the extent of 35 centimeter in, so this is then also here 35 centimeter upwards. The other parts of the alignment look good for the first run, and so let's do the calculation here, and the tendon of the phase 3 is also ready. Okay, what still remains is create the other tendons, and I can do again a multiple copy. Just do this tendon, and I have to define the starting point, which is here at 30. And Looking on the model here, I can see, yeah, all of them here are fitted, installed. I can recalculate that they are also in the complete 3D model inside. But yeah, things look fine. Yeah, so much for this topic here on this example for the plate bridge. As you can see, it's the way of modeling is quite the same like for link girder or for prefabricated elements or for normal 3D modeled elements. So you define some elements, you can copy them, you can mirror them, you can adjust them with the constraints, you can put accenters on it, and. So things are quite quickly then to create tendons out of it. Like in my case here, 15 tendons in about 5 minutes plus exclamation. Here I have another example where I want to show you in a quick manner a bit how to go with the certain accenters and other functions. So let's create first a tendon for this. Just a few points. So here I have it, and here I can go in and fit some extra accenters until the cable fits however I would like to have it. For example, in V direction, I put it in here, or I go in horizontal in U direction. VU you can see always here where is what and which direction is it going. I can fit it up, or also in this case I can work with the X accenter, so keeping the cross section the same location but adjusting the tendon point in longitudinal direction. So the point moves over here 1 meter further along and the spline is automatically adjusted. Or also can go backwards. It's always, I can go maximum from this one, I can go maximum to this cross section, or from here maximum over here. This is what is possible. Otherwise the program will give you a warning or a limitation notice. Yeah, so much for this one here. Now let's come to the examples, and here the first one is from Turkey, from Yüksekproje. It's the Rees Artwin Airport Bridge, which was completely designed in Allplan Bridge and Allplan Engineering. And I have here a couple of pictures from general overviews, formwork, reinforcement, and so on, different things which were done actually with the software solution. Here the reinforcement, and also the tendons were done in Allplan Bridge completely. The 3D alignment of each tendon was placed, and in Allplan Engineering was done easy to get the reinforcement on top of it, as the 3D planning in Allplan Bridge was already completed. Another example here from Portugal, it's a bridge made out of precast elements, so it was important to have the whole bridge first completely as one piece fitted. So in Allplan Bridge this was easy possible. Also tendons were completely set there in Allplan Bridge, and after this Allplan Bridge model was transferred, these individual blocks, as you can see here, were then detailed more and more in Allplan Engineering. Here one of these blocks, and here you can see also on the tendon, which are coming directly from Allplan Bridge, the smart placement of anchor blocks and so on, they are directly placed, so this was easy and smooth going. Also, as the tendon and the location, the whole thing was planned and set in 3D, the reinforcement was also easier to get in to its locations. Clashing and so on could have been avoided due to already precise 3D planning. Yeah, very impressive project. Here a next example is a cantilever bridge. As you can see here already the result in 3D with terrain and so on. Also it was done in Allplan Bridge completely and in Allplan Engineering. Here we see now the model in Allplan Bridge, and what was done in here, it's from the bore bars over bulk cap, piers, roadway and the main girder, everything is done already here. Also the abutments, as you can see, are completely modeled in Allplan Bridge already with bore bars and foundation and everything. Looking onto the tendons were modeled for the main girder but also for the piers, and in the main girder actually, as you can see here, we also have transversal tendons in there. Switching off the roadway and the main girder visibility, we see even more what is all done in here. And as you can see here from the construction process of the cantilever balance bridge, a lot of tendons are needed for the individual stages to be installed and set. Here you can see them. They are mainly fitted on the top and on the bottom of the girder, but also in the area of the pier there, it's necessary to have some transversal tendons in place. Here also a construction schedule was set in the project. As you can see, the whole construction steps from the bore piles over the pile cap, going then further on along the piers is modeled in here. The time difference between the individual stages and individual parts to be constructed are easy to see here in the Gantt diagram and also in the animation. As you can see, the left part, like span 1 and 2, they are constructed first and they're going in to be closed soon, while there's in the third, fourth, fifth span construction still ongoing. But this is good for presentation purposes, but the construction schedule here is even more powerful. If you decide to do also analysis in here, the construction schedule is the base where individual steps of interim construction are shown, and you can get outputs of inner forces and on the condition there. After transfer of the parametric model of Allplan Bridge to Allplan Engineering, we can see it also now in here. As you can see, all the elements here from the bore piles up to the roadway were transferred directly, and more than this, when I switch off the concrete elements, I can see here already all the tendons were transferred also directly, and addition on top of it, the smart part feature was used in this case. So at each end of the tendon there was the respective wished anchor block placed. So in this case, for this huge amount of tendons, the work was very quick because everything was done automatically by the program during the transfer for the main girder, but also for the piles and also for the transversal tendons. Everywhere is the anchor block placed what the user wanted to have in this case. So with this, I'm now at the end of my presentation and demonstration. At this point, I would like to say thank you to our clients and partners who allowed us to show parts of their projects. Last point of today is the question and answer session. And before we come to this, I would like to remind you, if you have questions, if you need support or help in future, please feel free to contact us via our support address. Okay, let's come to the questions in the chat now. If you have more questions, please write them now and I will try to answer them right away.